So in today's video, I'd like to talk about one of the components in the model, which is called residual connection or skip connection. And if we look at the diagram, it would be a set of this arrow and this added norm. So this set is called residual connection. And in my code, it would be these lines where I add input to the encoder and output from the multi-head attention. There are two main purposes to do. I use these technique. One of them is to stabilize the training. So when we normalize here, imagine we just passed the output from multi-head attention. Sometimes when the model gets deeper, if we stack encoder or decoder with multiple layers, sometimes model lose function to preserve information from earlier layers. So by adding output from previous layer, which is input to the current layer, to output from current layer, which is this one, the model would be able to preserve information from previous layers, and so it would allow model to refine already known representation to the input rather than relearning everything from scratch. So yeah, so sometimes when the model gets deeper, the performance sometimes degrades in performance. So this would just enable model to refine tiny representation rather than, like I say, relearning everything from scratch. And one of the another reason we use this technique is that it would improve gradients flow, meaning it would stop the model to suffer from gradients descent, vanishing gradient descent. So when the model compute back propagation from the loss, maybe loss would be around here through inputs or X. As the model computing gradients, as the model back propagate, like as it gets closer to inputs, the gradients get really small or even zeros, and if you use that to update weights, it was just hard for the model to generalize because you updated weights with really smaller not meaningful information. If the gradients get really small or even zeros, it means model didn't learn or failed to tweak the slope of the function. I mean, if the gradients get zero, as you get closer to input, you just failed to you would definitely fail to update weights. So you don't really want to do that. So by adding x, it would never, the gradients never vanishes. The reason is, so this is the y. I mean, this equation corresponds to these lines. And if we take out layer normalization, it would be y equal x plus fx, and computing gradients of the loss with respect to x, it would be dl by dx, and dl by dx is dl dy times dy by dx from chain rule. And since y equal x plus fx, dy dx is, so if we take partial derivatives respect to x, it would be 1. And with fx, dfx by dx. And this is what I've been talking, where gradients get vanished. So if the model is computing gradients and dy dx or dfx by dx gets really small or zeros, this dy dx is 0, and you use this to update weights. You just didn't update the weights properly, or the model has failed to. So if this happens in like you start back propagate from the loss to the x, and if vanishing gradients happens in these earlier layers, even vanishing gradients hadn't happened in these layers, the gradients vanished in this stage. That means the back propagation the model did in that epoch is almost meaningless. So by adding 1, even this gets zeros or really small values, you have 1. So the gradients never vanishes. So I think this is the main reason they do this. I'm not really sure. So I think this is it for today's video, just about this arrows and add a norm, and I tried my best to explain it. And I think I said this before, but I'm not really sure I'm gonna keep making this type of videos where I explain some topics in AI, because I've started doing, like, I've been trying to implement transformer model, and I also started a new project. So yeah, maybe it would be just me uploading devlog type videos where I explain what I've been doing, what I've done in previous days or last week, that kind of videos. Okay, I think this is it for today's video, and thanks for sticking to the end of the video, and as always, thanks for the other supports. Okay, thanks.